Okay, today we are going to implement a stack in Java. So a brief overview of a stack. Essentially, a stack is a data structure. It's a LIFO data structure. In other words, last in, first out, which means that think about stacking up plates on a counter. As you stack the plates up, if you then want to use one of those plates, the first plate that you're going to take is the one on the top. So that also happens to be the last plate that you would have put onto the stack. So in a stack data structure, the last piece of data that was put into the structure on the top of the structure is also the one that is going to be taken out first. We're going to use a sort of a test-driven development workflow here. I've created some tests in JUnit to check that our stack behaves as we expect it to. We'll be testing against these as we go along until all of the unit tests pass. Right now they won't compile because we haven't created anything. Let's get started. First of all, we need to set up the class. And we have public class stack, and this is going to be a generic type, and what that means is that when an instance of this stack is created by a user, they will get to decide what type of data is held in it. So we're keeping it generic, we're keeping it open at the moment, but it might hold strings, it might hold integers, it might hold some other type of object that's user defined. So within our stack, we're going to have a few different fields. The first one is actually going to be a nested class. And we're going to call this stack node. Our stack is going to have these stack nodes put into it. And each stack node essentially holds two things. It holds a piece of data. So that will be of type T, because we don't know what type it is yet. Whatever this is saved as, when we create an instance of a stack, that's what this will be. And we'll call that data. So a stack node holds the piece of data that you're trying to put onto the stack, and it also holds a pointer to the next stack node down. So if you imagine the top node, we're imagining that we're wrapping that in a wrapper that has within it the piece of data and something that tells us what the next thing is underneath, so that we keep track of what each item is within this stack. Okay. We're going to need a constructor for the stack node so that we can create new stack nodes. So to do that, we go public stack node, and when we create a new stack node, we want to decide what data is being put into the stack. So we're going to do that at this point. We're going to do that by having a parameter in the constructor for the data, like so. So the user creates a stack node, and within this parameter here, they decide what specific data is being put into the stack node, which then itself is going into the stack later. So we need this dot data equals data. This dot data refers to this here, this data field, which each stack node will have its own data field. And so this is being set to house data, which refers to this one. So whatever the user says is going to be the data for this stack node in this parameter, that's going to be set as the data for the stack node. One more thing we need to do is to set the next pointer, this one here, to null to start off with. So obviously as we build up the stack, the next pointer needs to point to whatever the item underneath it in the stack is. But just to initialize a new stack node, we're going to set that to null just for good practice, and we can change that later. Okay, so we now have this class called stack node, which is itself going to be one of the fields of stack. We need one more field within stack, and that is going to be a pointer to a stack node, and we're going to call it top. So what this field does is it keeps track of the stack node that is at the top of the stack, so that we know which one we're pulling out first. Now that we have our fields done for the stack, we need a constructor. So public stack and when we initialize a new stack, we want it to be empty so that we can just start adding stack nodes as we need. The way that we're going to tell that a stack is empty is that this top node here is going to be is essentially going to be null. If that is null, that means there's nothing there, so we know that the stack is empty. If you have a stack of plates, but there is no plate at the top, then there must be an empty stack, because you have to have at least one plate at the top of a stack in order for there to be a stack in the first place. All we need to do here is say this.top equals null, and that will initialize this new stack with nothing in it. We have a class here with some fields, including a stack node nested class, which itself has some fields, has a data field and a next field. And we also have another field within the stack called top, which is going to keep track of what the top stack node is in the stack. And we've also made constructors for the stack node and the stack. Now we need to start thinking about the methods. The first thing I'm going to do, which sort of lines up with this test-driven development idea, is I'm going to create the skeleton of each method that I want to implement. That way, when I run that way, I'll be able to run the tests that I've written. The tests will most likely fail at this point, but I can at least run them, and then I'll be able to check gradually as I do more of the implementation whether I'm passing those tests. So there are a number of methods I want to implement. The first one is a helper method. I'm going to call it isEmpty. What this does, first of all, it's a Boolean method, which means it's going to return true or false. So what this method is going to do when I've written it, it's simply going to tell us whether or not the stack is empty. And the way that we tell if a stack is empty, just as a recap, is if the top is null, then it's empty. So honestly, I think I could just write this one now rather than having just the bare bones of it, because all we need to do is say top return top equals null. And if this statement here is true, then isEmpty will return true. If it's not, it will return false. And that way we can keep track of whether or not our stack has anything in it. This is a non-essential method. It makes it's going to make our code more readable, because we could just write top equals null if we want to check if something's empty. But it's much quicker to understand isEmpty. We know what that means just from reading it. So now that we've done isEmpty, let's see how our tests are looking. We've still got to write the test called push, and one called peek, and one called pop. So I'm just going to write the bare bones of these. First of all, push. Push needs to push some data onto the top of the stack, and that is going to need a parameter of type T called data. I can leave that one empty because it's void, it doesn't need a return type. So for now I'm just going to leave that empty. But the job of push is to put some new data in the form of a stack node into onto the top of the stack, and we'll look at how to implement that shortly. We need public t pop, and pop does need a return value. For now, I'm going to say return null. The job of pop is to take the top element in the stack, take the top piece of data and remove it from the stack and return it to the user. After calling pop, the stack should have changed. It should no longer have what the top element that was there before on the top, and the method itself will return that top element to the user. We'll implement that in a minute. We also had public t peak. Now peak is similar to pop but a little bit easier. What peak does is it returns the top element of the stack to the user, but it doesn't remove it. So this simulates the idea of just having a sneak peek at what's on the top of the stack, but it doesn't actually change the stack. We're not removing it from the stack. Okay, so we have all of the methods we need, and you can see that this is no longer red because our tests should be able to run now. All of the methods that it's looking for exist. So if I run our methods, let's see what happens. Excellent. So we have some failing methods, which is exactly what you would expect. Most of these methods, most of these tests at this point don't work, except for one. New stack should be empty, because if you remember, when we initialize our stack with this constructor here, we are setting top to null. This test is checking once we've created a new stack, that stack is empty. Is empty, if you remember, we've done that one here, and it just returns true or false, top equals null. What didn't work? One item added should show on top. This method, this test here is going to require us to implement push and peak. Peak is a nice simple one. Peak is just looking at what that top piece of data is in the stack. So we need to return the top. This stack node here, top, points to that top piece of data. So essentially we return top. However, this won't work because this is not the type that we are trying to return. This is a stack node. We are trying to return the data within the stack node, and that is a field within each stack node, this field here, data. So what we need to do is return top.data. So now peak is implemented and should return the piece of data that is held at the top of the stack. This here won't work still because we haven't implemented push. So it cannot read the field data because this .top is null, which means it's empty. There's nothing there. And the reason is that we haven't pushed any data into it. Let's implement push. Right, there are two scenarios for push. Push is going to add a piece of data to the stack, but there are two possible conditions here, and our implementation depends on which is true. In one instance, the stack is empty, but then also we're going to have a slightly different implementation if the stack is not empty. So we have here two conditions. If stack is empty, we want to do some stuff, and if stack is not empty, we want to do some different stuff. So how are we going to write this programmatically? We need an if statement. So if, and we can say quite simply, we've already written this method here is empty to do this. So we're going to say if is empty, we want to do whatever is in here. Then we could put if not is empty, so using the negation operator here to do this second condition. However, much simpler. We can write else just to clarify that bit. So now we have if is empty, we're going to run whatever's in here. Else we're going to run what's in here if it's not empty. Now, first of all, right, so now we've got these two conditions here. We're going to need a new stack node, and that's going to go above our conditions. This new stack node is what we're pushing onto the top of the stack, and it needs to have within it this data. Let's create our new stack node. I'll call it new node. Equals new stack node, and this needs to have data. So this data here is the parameter that we've put in here. If the stack itself is empty, then new node is what we're going to assign to the top of the stack. So top equals new node. And that's all we need to do for now here. It was empty, we put one thing into it, that thing is at the top. Let's move on to if the stack is not empty, which is just ever so slightly more complex. For this one, what we need to do, we've got our new node, and we need our new node to essentially take the place of the top node. Whatever's at the top has this next field, which is here. And next points to what's underneath it. If our new node is going to take the place of the top node, it's essentially going on top of top. And therefore, its next field needs to point to top. So we go new node dot next equals top. So this line of code here is saying that the next thing down from new node is going to be the top. However, there is one more thing we need to do, which is we need to take the top pointer and now move it to point at new node itself. So top equals new node. So we now have two situations here. First of all, we're creating a stack node, and then if the stack that we're trying to put this new node into is empty, we simply put it at the top. If the stack's not empty, then we take our new node and we have its next field point to the thing that's at the top currently. We then move the top pointer to our new node so that our new node is registered as the top, and then the new node's next field points to what used to be the top. Let's see how that looks in our tests. Let's run all of our tests again to make sure that this previous test also still passes. Okay, so as expected, obviously there are still some errors in some of these tests. However, 3 tests now pass. New stack should be empty, that was passing anyway, that still passes. One item added should show on top. So when we add one single item to an empty stack, that shows on top. 2 items added should show top item. So when you add 2 items to a stack, when you use peek to look at the top value, it should show the last thing that you put onto the stack. So what's not passing? Pop should remove top item. And of course, because we haven't implemented pop yet. So pop was that other method here, which was a bit like peek, but more complex because we have to actually remove the top item as well as returning it to the user. How do we implement pop in a stack? We need to do a few things. We need to make sure that we don't lose reference of data, so we don't lose track of any data. First of all, we need to get that top item and we need to save it somewhere new, so that when we change what the top is, we've still got a reference to the old top item. And this is exactly what I'm going to call it. I'm going to create a new stack node pointer and call it old top. And that equals top. So old top is pointing to the same thing as top. So now even if we change top, which we will have to do because top needs to point to essentially top.next, so the next thing down underneath the top item. And when we change that, old top will still be pointing to the thing that top used to point at. So we've still got something to reference, that old top item that's going to be removed from the stack. So now top needs to be changed. We need to actually remove the top item from the stack. And the way we do that is by changing some pointers around. Top equals top.next. So now we have old top, which is holding the thing that used to be the top. Top has been changed to the second item down, which is essentially the same as removing the top item from the list. And now we need to return that old top item to the user. So there's a slight issue here, and it's because the return type is T, so it's whatever the data is that's held within the stack node is what we want to return to the user. Old top is actually a stack node, not the data held within it. So we need old top.data to fix that. Okay, let's run our tests again and see how we do. And we have all 4 tests passing. So our stack is able to initialize a new stack, and that new stack is empty. When we add one item, that item shows on top. When we add 2 items, the top item is the last one that was added. And when we call pop, we do indeed remove the top item. All 4 tests pass, and we have here a successful stack implementation in Java.